Hi, welcome to another practical session of spatial statistics and spatial econometrics. We're working with the R programming language. My name is Saif, and the topic for today is kriging and cross-validation. We're working on acquiring programming skills for spatial statistics, but acquiring these skills is founded on our understanding, solid understanding of the conceptual material. And for today's session, you will need to know what a model fitting procedure is. You will have a good understanding of what it means to fit a model and what it means to fit a model variogram, which is something that we did in the previous session. You will need to remember, at least have a passing recollection of Kriging estimators and Kriging equations, the process of Kriging, what does it mean, what does it do, and of course know what ordinary least squares is, which is not necessarily covered in this course, but this is something it will be helpful for you to know because this will be using it in today's session. For programming skill-wise, in the previous session, what we did was we estimated and fitted variograms using two data sets, using the MUSE data set as well as the Western UP groundwater level data sets. And this is something that ideally, hopefully that we're very comfortable with because we're going to build on this today. What will we do today? So we will look at the parameters of our fitted variogram. So the main parameters that kind of tell us the shape of our fitted variogram, and these are called SIL, nugget, and range. I hope you know what those mean. If you don't, please refer to the appropriate video and review that material. And then we will use our fitted variogram to perform kriging, spatial prediction with ordinary kriging. Yani we will try to predict the values of groundwater levels at locations where we have no data from the observed data. And then we will cross-validate our model variogram selection. So we will provide an additional way to quantify or to measure how good the selected model is and how much agreement there is between the predicted values and the observed values of groundwater levels. If that's clear, if some of that is not clear, please pause the video now and go back and review the material. If that's clear, let's move ahead. So remember, this is as far as we had got last time. This set of blue points is your experimental variogram for groundwater levels. This line is the fitted model variogram for which we used a spherical variogram model. Now, what does this give us? Why does it help to have this kind of smooth line fitted to these points? Well, now for any value of h, even between these points, we can get a value of semivariance. So we know for any separation, any two locations, no matter what their separation is, whatever the value is, we will get a value of covariance or variance between those two locations. So we have a kind of spatial structure over the whole region where we can select any 2 points arbitrarily and get a value for the variance between the groundwater levels at those two locations, no matter where they are. So this is a powerful kind of information to have, and we can use this for spatial interpolation using the Kriging estimator. I'm not going to go into those equations. Of course, I expect and hope that you will be familiar with them. So let's move on to our coding session. So here we are. We had fitted a spherical model variogram, and we had stored it in an object called LZN. Still using LZN, which is log of zinc, where I should be using GWL. So please pardon me for that. The objects should be correctly named to reflect what they contain. So LZN dot fit. So we want the spherical fitted model. So if we just print that out, it gives us, so we can also look at it by clicking on it here. So it gives us some information. So it gives us a kind of 2 by 2 matrix, and in row 1 we have something called nugget or NUG for short, So this value is the nugget effect. So it is basically this value here, where it crosses the y-axis. And the nugget effect, which is the variance at spatial lag 0. So typically there should be no variance, but because of the fact that we're estimating things from data, and we fitted something to a data which is not exact, we get some residual variance even at 0 spatial lag. And this is called the nugget effect. And roughly for us, the value is 2.2 or so. And then for the spherical model, the partial sill, this is the maximum value that the variance sort of reaches. And the partial sill is at about 42. So the sill is where the variogram, the variance increases as spatial lag increases. So as we go further away, the variance between observations, the observations are more sort of at variance with each other. And that continues to increase, but at some point it doesn't increase anymore. If you go further away from that point, then there is not necessarily any increase. You kind of reach a global maximum variance. And this is a very classic sort of structure that we see in spatially autocorrelated data. So the value of this maximum variance is something like 43. So that seems right. It's right about here. So one thing to do is to just compare this with the sample variance. So we can compute the sample variance of the post-monsoon and remove the missing values. So the sample variance is something like 41. So this is good news, because the variogram, what the variogram is telling us, the value for the variance of the whole sample is the same as this global variance that the variogram reaches ultimately. So that's good agreement between our variogram and a different estimator for the global variance. And then this parameter here, range, this is the distance or the lag at which the maximum value is reached. And this is about 0.26, which is right about here on the x-axis, 0.26. So 0.26 units of distance. So what that means is that this is the range of spatial autocorrelation. Yani the values of groundwater levels are correlated within this range. So if you have a well somewhere, then you can expect that in this radius of 0.26, the values will be similar to what the value is at this particular well or this particular location. And then beyond that, we don't expect not necessarily to be that similar. And the similarity, of course, varies. At 0.1, it will be very similar, whereas 0.2, a little less similar. Beyond that, not necessarily similar. So those are the three, the nugget, the sill, and the range are the three parameters that kind of tell you the shape of the variogram, and these three parameters are very important to know. And the way to know them is simply by, you can just type the name of your fitted variogram object. So let's for a moment see what it is for the exponential model. So for the exponential model, you get a slightly larger sill, which is close to 50. So we had 42. And then for the range, you have 0.13, which is kind of half the range of the, and the nugget is 0. So that's good. It actually gives you a nugget of 0, which is what you theoretically expect. However, notice that the range is half of the range that the spherical model. So your choice of model really alters the parameters and the estimates for the parameters. So you should be careful. Of course, we saw that the spherical model was a better fit. So since it was a better fit, we selected that. So we trust these values, the ones for the spherical model, a little more. All right. Now that we have this model variogram, we want to go further. So we want to actually, so if I just show you the map, we have this data, right? We have this data, but this is not a lot of data. This is quite a large region. We have roughly 200 or so wells, 250 wells. We want to know the groundwater level in between these wells as well. So what we want to do is we want to spatially predict, knowing the values at the observed locations and the structure of spatial correlation, spatial variance that we've estimated using the variogram, we want to predict statistically the values of groundwater level at all points in this region. So we will need a different kind of spatial object for that, which is called a spatial grid or spatial pixels. So we will have a grid of values, and then those, we will estimate the values of groundwater levels. We will predict the value of groundwater level on each point in that grid. So let's go ahead and make such a grid, and that is done using this code. Create an empty grid where n is the number of cells. So this is 200,000 cells. It's a very high resolution grid. You don't typically need such a high resolution, but I like to have good quality predictions. So or rather good resolution in my predicted output. So I used a lot of points. So we can go through this, and this is the same thing. We need to provide the coordinates, and then at the end of this, we get an object called GRD, which is a spatial grid object. So if you say class GRD, it's of type spatial grid. So it's a different kind of spatial data. So far we had spatial points, spatial point data frame. Now you know of a different kind of spatial data. And then we need to project this grid to the same projection system that we had for the wells. So let's go ahead and do that, and then we can use this function called Krigg. So this is named after somebody called Krigg, who first proposed this technique. Now this function is new, so let's go through the parameters. So the first one is a formula. So we want to predict the post-monsoon groundwater level with, again, a constant mean assumption. We're assuming constant mean stationarity. And then we want to subset our data with only the observations which are not missing. So this is not necessarily necessary for us because we had already removed missing observations previously. We could have just passed in the data. And then we pass in the grid that we just created in the lines above, and then our fitted model variogram. So it needs the formula, it needs the data, the observed values, which is these blue circles, the grid on which the prediction will be performed, and the fitted model variogram using which the prediction will be performed. So if we go ahead and run this, it is using something called ordinary Kriging because we used a constant mean assumption. So we got a warning, that's fine. We can ignore that for now, although one should typically not ignore warnings. So it doesn't like the use of is and a, so it doesn't like this line. So I think if I just remove this and just pass in the data, hopefully that will just go away. If I just remove this, yeah, okay, so that went away. All right. So now, so now we have a spatially predicted groundwater level data set where we have a value for every point on a very dense grid. But the thing is, we need to be able to actually see it. So in order to plot this, I've added two functions, map predicted groundwater level and map variance. So what this does is, if I pass in the Krigg object, the spatial grid, it will give me a map of that grid. And I'm not going to go through this code. I encourage you to look at it yourself. This is using the raster library and the tmap library, some of which you're already familiar with. In the interest of time, I'm going to call this function map predicted groundwater level and pass in my Krigg object. Could not find function raster. Yeah, so this is the reason. We have to load our libraries. We never loaded our libraries, right? So it couldn't find the function. The raster function is available inside the raster library, so we needed that. Now that we've done that, let's try and, okay, so there you have a, excuse me, you have a crigged or a spatially interpolated or a spatial prediction of groundwater level over the whole region from a set of 250 or so observed values. And we see that there is a large sort of hotspot of depletion around Baghpat, and then one around the urban area of Meerut, and for the rest, the groundwater levels look a little better. Now, this is a statistical prediction done using the Kriging estimator, so typically we expect to have a variance value for every one of these predictions. We need to know how confident we can be of this prediction. So what we can do is we can also map the variance. We can map the variance of each prediction, and we're using the same object, and this is a map of variance. So you can see the darker reds mean higher variance, and I'll show you why exactly there is darker red along the edges and slightly light. So basically what this is saying is that we can be more confident of our predictions where there's lighter red colors, and a little less confident where there's more red, and really not confident at all when there's, you know, sort of deep red shade. So this is just a measure of how good our prediction is. So let's go back to this for a while, and now let's look at what we've done. So we started with this data. This was data that was, somebody went out there to an observation well, lowered a tape into it, measured the groundwater level in the year 2015 at 245 locations in post-monsoon in this western UP region. And we took that data and we applied a geostatistical model, and using the variogram that we estimated from this data, we estimated the structure of spatial variation, and we spatially predicted purely in a statistical, from a statistical point of view. We haven't gotten into any hydrology. We don't need to know what the subsurface flows were like. We don't need to know anything about the process. I mean, we do if we want to argue about stationarity, but our prediction is done purely with statistical methods, geostatistical methods. We prepared this map, and of course, as you can see, the circles are a bit bigger here in Baghpat, so we expect these predictions to be also larger, and then circles are a little smaller. Now see if the variance here is very high. Well, that's because in Ghaziabad we don't really have a lot of data. So if we don't have a data, we're not going to be very confident of our predictions, which is what this variance is telling you. So if your prediction variance is high, then you need to be careful about what you use the data for, and how much confidence you can place in your prediction. So this is very useful to have, and this is something that you don't have with physical spatial interpolation methods like inverse distance weighting or other methods which are deterministic, which are not statistical in nature. So having said that, let's go back to our code. Now remember, we had computed the sum of squared errors for our fitted model variogram to see how good the fit is. We have one more way after we've done prediction. What we can do is we can do something called cross-validation using a command called krig.cv. And cross-validation, what it does is it basically takes out one observed value of groundwater level, predicts it using the rest of the data. So then at that location, you have an observed value as well as a predicted value. So you can compare how good your prediction is with what was observed. And this is sort of often used in the research literature to, estimate how well you've done with your model selection and model fitting. So let's go ahead and do that, and then let's regress our predicted values on the y-axis on our observed values. So if you look at the object produced and you look at the data, we can just look at the data. It returns an object called lzn.cv, and we can look at only the data of that object. So you have a predicted value in the first column, var1 dot predicted, and then var1 dot var. This is the prediction variance, and then the observed value at that point, and the residual when you and the z-score of that residual. So what you can do is you can plot the predicted value on and the observed value. So that's what we've done here. This is a scatter plot of the prediction versus the observed value, and then you can regress this and draw a regression line and then try to get a summary. So you can see that the slope of this line is about 0.63 or so. So ideally, we want the prediction and the observed values to be exactly equal, but we find here that on average, the predicted values are less than the observed values. They're really about 63% of the observed values. There is some underestimation. We can also perform a correlation test between the predicted and the observed values, and we see that the Pearson correlation coefficient is 0.77 or so. So the values are highly correlated, but there seems to be some underestimation. So if you wanted a better cross-validation, if you wanted more agreement between predicted and observed values, you would have to go back and question some of your assumptions, some of your methods, some of the choices of model, and some of the parameters that you used to achieve a better fit. And this is all something, these are things that will be gained by experience and your understanding of geostatistical modeling. So just to summarize what we've covered today, we looked at variogram parameters, SIL, nugget, and range. And these are the parameters that kind of parameterize or tell you or contain the shape of the variogram function. They each have a meaning, and we saw visually how we can plot them as a graph in R and what each of them means. We also performed spatial prediction using ordinary kriging. We made a constant mean assumption, and we performed ordinary kriging, and we used that to create a map of groundwater levels over a region of a sub-region of Western Uttar Pradesh. And then using kriging, we tested how good our model selection was by cross-validating our spatial prediction. So, and the way that worked is you predict one value at a time. So you go to a place where you've observed the groundwater level, you remove that value from the data set, so you have an observed value at that point. You predict the value at the same location using the rest of the data, and then you compare the predicted value with the observed value, and that gives you a sense of how good your model selection is. You can repeat the same process with another model and compare how good the agreement is between your predictions and your observed values, and that gives you a measure of which model to select for your particular research task. And that's what we did in this session. We'll see you next time. Thank you for your attention.